Hi everyone, my name is Britteny Backus, and today I'm going to be giving you a presentation on the astronautics, the physics of spaceflight. So the purposes of this presentation is I am very interested in rockets, and there's no astronautics class taught at UMW, so over the course of this semester, I did research with my physics professor. So the topics of this presentation are going to be the basic principle of rockets, some of the complications that show up, and how do we make rockets go fast. So firstly, we can start out with the basic principle, which is the conservation of momentum. And momentum is conserved, meaning that it can not be created nor destroyed. And conservation of momentum tells us that momentum always has to be zero, and this is what makes a rocket go forward. And to show you a visualization, we can move to the first figure, which is before ejection, meaning that momentum is equal to 0. Then, in the after ejection case, which is just below that, we've kind of thrown some stuff out of the rocket, and the stuff being thrown out of the rocket has a velocity of v sub ex, which is velocity of the exhaust. So this exhaust now has some backward momentum. However, total momentum has to be 0 by the conservation of momentum, meaning that the rocket must have equal forward momentum to cancel the backward momentum of the exhaust, keeping the total momentum 0. Thrust force exists because the conservation of momentum, and the thing that is important for us is that it involves the velocity of the exhaust. In simpler terms, the faster we throw stuff out the back of the rocket, the greater force we apply on it to move forward. And we can just quickly go over the equation, which is equal to mass times velocity of the exhaust, and velocity of the exhaust is the rate at which stuff flies out the back, which is kilograms per second. So in this figure, the spacecraft is already in space. However, in reality, we need to take off from Earth first. So how did we get the rocket from Earth to space? Next, we can talk about the force equation, which is equal to F star plus force of gravity. Well, F star is the only force that we can control, and we're going to add that to the force of gravity. Well, the force of gravity is the only external force, therefore gravity pulls down the rocket, so the rocket has to travel at v escape. What is v escape? Well, that is the velocity of the escape, and it is the minimum amount of speed any object needs to go in order to leave Earth's gravity pull, and in our case, the object is the rocket. And we need to overcome v escape. Well, gravity is going to act against F star. Well, the minimum amount of speed is 11.2 kilometers per second, and we need the speed of the rocket to be greater than that, which is of course our goal. So to make the rocket go faster than v escape, we want the exhaust to go as fast as possible, which is what makes the rocket go faster, as I previously discussed in the past slide. So how do we make the exhaust shoot out as fast as possible? Well, imagine that these atoms in the figure or the video that I'm showing you are the atoms of rocket fuel sitting in the back of the rocket. We heat them up. As you see what's happening, they're speeding up. Heat gives speed to the atoms, but as you can see, these are all in totally random directions. We need them to go straight out the back, so how do we make them go in the correct direction? One of the main ways that we can get these molecules to go in the direction that we want is, of course, the shape of the nozzle or the chamber. So first you can see in figure 4.1 the combustion chamber, which is here. This is where the explosion happens, and then it kind of goes in that forward direction out the velocity of the exhaust, which is here. So next we can move into this slightly less complicated image just below that. As you can see, the red square is the nozzle, and then before that we have this black dot in the thrust chamber, which is the stuff that we want to fly out the back. Well, these blue lines are the direction or the flow in which we want them to go, which is the most ideal. And the narrowest part, which is the throat, or if you know physics, this is Mach 1. And that part of the nozzle, or the chamber, is where these molecules are going to hit the speed of sound. Anything past that, they're going to exceed the speed of sound, which is the velocity of the exhaust, which is the stuff out the back. And in all, this is the flow of which stuff is going to fly out the back, which is, of course, the most ideal. And as you can see in figure 4.3, is a little bit complicated to explain, but I'm just going to give you the basics. What essentially this figure is saying is that the higher the pressure and the higher the temperature, and temperatures measured in kelvins, the higher these two, the faster the speed will increase, and the velocity of the exhaust is going to be higher as we go through the nozzle, which is, of course, the most ideal. But what does an ideal rocket launch look like? Well, first I'm going to show you a simulation of an ideal rocket engine launch, which this is just a simulation, so it's not attached to a rocket, and this is going to kind of show you from random to directed energy, and the shape of the nozzle would force the molecules to go in the forward direction. And just a little bit of a warning, this video is quite loud, so I would advise to turn your sound down, and I'm going to show you. And as you just saw, these are going in the direction that we want for an ideal rocket launch, because these are flowing through the nozzle and exceeding the speed of sound. And again, with a large pressure and a large temperature, this increases the speed of the rocket, which is ideal for a rocket launch. So what is the equation of an ideal rocket launch? So first we have the rocket equation of motion, which is delta V, or the change in velocity, and we equal that to delta velocity of the exhaust, which is the change in the velocity of the exhaust, which again, that is the speed at which stuff flies out the back. We multiply that by ln, or if you're more familiar with mathematics, that's the log, and we take that log and multiply it by m sub 0, which is the mass before the ejection. We divide that by m sub f, which is the mass after the ejection. So then we have the speed of the rocket as it's launching, which is the change in velocity again, and we equal that to the initial velocity. And we subtract it by all this stuff, in which is a little bit too complicated to get into, but this just means that it's the gravitational loss. So the difference in these two equations is that the first equation that I talked about, which is the rocket equation of motion, there's no gravity present in this one. But the second one, this is the gravitational loss. And if you didn't know, gravity is equal to 9.8 meters per second squared. So again, our goal is to have the velocity of the escape be the minimum amount of speed that we want, in which the change in velocity, or the speed of the rocket, is going to be greater than that, which again is 11.2 kilometers per second is the lowest that we want the speed to be. So now we can make delta B bigger than the velocity of the escape. Next, I want to show you a visualization of an ideal rocket launch, and in particular, this one is the space shuttle launch, in which you will see that this stuff is the velocity of the exhaust coming out the back, and this has a backward direction in which moves the rocket forward. And again, the faster the stuff out the back, the faster the rocket will move forward. And for complications and purposes of this video, I won't be talking about in great detail, but we do have rocket staging, and this also is not shown in the video, but this kind of picture on the right shows what happens during rocket staging. So in conclusion, or to summarize this presentation and everything that I just talked about, we can say that the velocity of the exhaust would make the rocket move in the forward direction. However, gravity is what is going to slow that down. Then we can say that we speed up the exhaust by the explosion of the rocket, which is shown in those videos that I previously showed, which is kind of the stuff flying out the back, which again speeds up the rocket. We then talked about how we can direct the exhaust, or the molecules, instead of them going in different directions, which is not ideal. And we can say that we use that from a supersonic nozzle, which is the most ideal nozzle, which supersonic is the reason you hear that kind of boom when a rocket is launching. And then the rocket equation tells us the speed of the rocket, which is kind of how fast the rocket is going, which is delta V sub 0. And then for purposes of this presentation that I did not cover due to time, there's much more complicated stuff, and therefore I just kind of explained the basic stuff of a rocket. And I want to thank you for watching this video and taking the time out of your day, and I hope you have a great rest of your day.